Hello, we are going to discuss fluid mechanics, and this course we are going to take in great detail, and we will not go through the shortcuts. And the students who are really interested in going deep into the subject of fluid mechanics can follow the course. So, first of all, moving through which topics we are going to cover in this course, I will explain that. So, course contents. First of all, I will go through the course contents. Course contents. So, this is the course on fluid mechanics. Fluid mechanics for undergrad. Undergrad students, and the topics that we are going to discuss are first the introductory concepts of fluid mechanics. Introductory concepts. This introductory concept will include the basic continuum hypothesis, basic concept of viscosity, surface tension, and maybe one or two topics according to the requirement. After this, we will move directly to the second topic of this course, which will be fluid statics. Third topic of this particular course will be, after studying fluid statics, we will move on to fluid kinematics. Fluid kinematics. The fourth topic of this course will be in dynamics of inviscid flow. Dynamics of inviscid flow. In this we will study Bernoulli's equation and all, which is valid for the inviscid flow. After this, we will study the integral form of control volume. Integral form of control volume. And we will discuss some of the problems also related to the integral form of control volume. After this, we will move to the dynamics of viscous flows. Dynamics of viscous flows, which for Newtonian case we will discuss all this. So I will go through Navier-Stokes equation in this. The point to be noticed here is there may be different kind of equations that we can get from the different constitutive relations. For the Newtonian case, if we put the constitutive relation, we get Navier-Stokes equation. But if the fluid is non-Newtonian, maybe the different fluids which are non-Newtonian fluids like Cassicus or Allroyd B, we can have some different relations which are not which is not called Navier-Stokes equation. Navier-Stokes equation is equation which is valid for just Newtonian fluid, because the constitutive relation we are using in the generalized form of the momentum conservation is for Newtonian. So Navier-Stokes equation is valid only for the Newtonian fluids. We will discuss how non-Newtonian fluids, for the non-Newtonian fluids as well, how we can use the momentum balance equation. Okay. So just for getting idea, which is not the part of this course, but for getting idea how the equation, momentum balance equation looks for non-Newtonian fluids, we will discuss some examples of non-Newtonian fluids as well, for sake of comparison. After this, the next topic will be turbulence. Or turbulent flow. So after turbulence, we will discuss boundary layer theory, boundary layer theory, and after boundary layer theory, we will discuss flow past immersed body. Flow past immersed body, and then the next topic will be pipe flow. In the section of pipe flow, we will discuss some of the engineering implications of pipe flow and how the different engineering parameters comes into the play. And after that, the next topic will be dimensional principles of similarity, principles of similarity and dimensional analysis. The term dimensional analysis is going to be very significant in the course of fluid mechanics, in the course of transport phenomena, because dimensional analysis makes the calculation much simpler. So we will discuss why dimensional analysis is very important for solving the problems, which can simplify our problem up to a great extent and reduce the mathematical complication of any problem. And the last topic we will discuss will be the fluid machines. Fluid machines. This is the total content that I'm thinking of providing in this particular course, and this is generally useful for the students of second year undergrad students. The course may be a little bit tricky for the students of second year, but I will discuss some concepts of mathematical preliminaries, like I will discuss mathematical preliminary, which will include tensorial algebra, as it will be required in the due course. Wherever tensorial algebra will be required, I will be discussing that particular part at that particular section only. I will not discuss entire tensorial algebra or mathematical preliminary all at once, but as I will require these particular things, I will discuss it there. And in this I will discuss Einstein's notation or index notation, or index notation. The students who want to complete this course within very short interval of time, they should not go with this particular course, because it may take time and you have to focus more attention on the course. We will go rigorously through the course. The first thing, this is the course content, and the first thing that I'm going to discuss in the first as a first topic is just a general concept, like I have discussed introductory concepts. So the first concept is the Knudsen number. Knudsen number. What is Knudsen number? Knudsen number is defined as lambda by L, where this is written by Kn. This is equal to lambda by L, where lambda is the mean free path. Lambda is mean free path, and L is the characteristics length of the system. characteristic length of system. Suppose I have a channel like a plate, a top plate and a bottom plate, and there is it is bounded from the left side by a wall and from the right side by a wall, and there are certain number of molecules in between. If these molecules are moving randomly in this particular given space, then they are going to collide, and due to their collision, uh, there will be a certain length associated with their collision. After moving, suppose I have this molecule 1 and this molecule 2, there will be certain distance traveled by a molecule 1 before colliding with certain different molecule. So the length that is traveled by a molecule 1 or molecule 2 or any molecule in this system is given by is called as mean free path. And the characteristics length of the system is given by, suppose the length of this system that I have defined is L1 or L, and the width is W, and suppose both are of the same order, then L or W, L is a off order of W, then L or W both can be taken as the characteristics length of the system. They are the characteristics length. So if the system that we have taken, this is the system, is much densely packed, then the probability of molecule of interacting with each other or colliding with each other will increase, and the length lambda will decrease, so the Knudsen number will also decrease. So for a more dense system, the Knudsen number is very small, and for the less dense system, the Knudsen number is little bit larger, or even it may increase, and the Knudsen number can be of order of 1 as well when the length characteristics length of the system becomes of order of the mean free path. Suppose I have a system in which I have this system and I have only 2 or 3 molecules in between. So the length that is traveled by a molecule before colliding may be of order of L, and in that case I will get Knudsen number to be very large. But generally for a very dense system, the length that is traveled by a molecule is much smaller compared to that of the system length, system characteristics length, and in that case Knudsen number is very small. So if Knudsen number is very small, this implies the system is densely packed. System is densely packed. And if Knudsen number is large, then system is rarefied. Now, if the system is rarefied, for any differential equation, the use of differential equation for that particular system will become very difficult, because differential equation is equation which is valid at each and every point of the domain. So in order to use differential equation for any system, it is required that the property or anything associated with the system is defined everywhere pointwise. If the system is rarefied, we are not able to use the governing differential equation, which you might have seen, the Navier-Stokes equation or Euler equation or any kind of equation will not be valid. So it is required for system to be more dense and Knudsen number small, every property must be defined in order to use the differential equation comfortably. The second topic after this Knudsen number that we are going to discuss is little bit tricky, so I will write this. The concept of traction vector. Traction vector. Now traction is like I will explain later that it is a vector or tensor. I will go into the detail of this, but for now let us say as a traction vector. Suppose I have any surface, and on this particular surface I have taken a differential area which is having a magnitude dA and oriented along some direction d. oriented along some direction, and df is the force which is acting on this particular area. Df is the force. So the traction vector is defined as, this is traction, df divided by a, dA. df divided by dA. df is the force acting and dA is the area associated. Now the df is also a vector direction, because force is vector quantity and area is also a vector which is a vector quantity. So in this case the traction is not just a vector, but it will be identified by using two different indices. The first index, in suppose I write it like this, tin. N and I are the two different indices denoting the area and the force direction. This is traction. And since there is presence of two different indices, it is called tensor. Vector is also a tensor of first order, and this is the second order tensor, because I have two different directions associated with this. So this is df divided by dA. Traction vector is df divided by dA. For any quantity, if I underline this at the bottom, this represents it is a vector quantity. It is equivalent of this, which is commonly used in the high school physics or so I will use the line below the letter in order to identify that a quantity is a vector quantity. So there are two different indices, I and N denotes these are the two different indices. This implies it is a tensor. There is no only one index associated with traction. There is two different indices associated with traction. So let us try to understand how I can write this tensor on the different areas. So suppose I have this is x-axis, this is y-axis, and this is z-axis, and this is the element that I have taken. This is the element, and the element that I have taken is of shape of cuboid. This face is oriented along a positive x direction. And one more thing I would like to say, x is represented by index 1, y will be represented by index 2, and z will be represented by index 3. So wherever I will write 1, it means it represents x. Wherever I will write 2 will represent y, and 3 will represent z. Subsequent in this course. So one more thing I would like to say, the first index, whatever I will write, will indicate the direction normal, means the direction of area, direction normal, and the second index that I will use will represent the direction of force. I have said that there will be two different indices associated with a tensor. So traction is a tensor which will have two different indices. The first index will give the direction normal or the direction of area, and the second index will give the direction of force. So this is x, or this is represented by 1. This is y, or it is represented by 2, and this is z, it is represented by 3. This is any element that I have taken whose this area is pointing in the positive 1 direction. Okay, so if I have to write the traction I have written as TIN, or it can also be written as TNI, like this as well. The first index N is representing the direction of area, and the second index I represents the direction of force. Okay, so this we need to keep in mind. So if I have to write, the first index gives the direction of, this is tau, the first index gives the direction of area. So area is oriented along direction 1 and the force is directed along a1. So it is given by tau 1 1. Now for this particular force, suppose I want to write, how I have to write this. So the area on which this force is acting, which area this force is acting, it is acting on area which is oriented along positive one direction. This is the positive one direction. So this force is acting in positive one direction, so tau 1, and the direction of force is along y, so the second index will be 2. In this way I can write the direction and the shear stress or the stresses acting on the different surfaces. Suppose I want to write on this particular surface, the area of this surface is pointing along negative I direction. This is negative 1 or negative I. So if I write tau, the area is oriented along 1 and the force is oriented along 1. One thing you should keep in mind, that if area is oriented along the negative direction, the force will also be oriented along the negative direction. If area is oriented along the positive direction, force will also be oriented along the positive direction. For the first case, we have seen that on this surface A, B, C, D, suppose, we had the area oriented along positive one direction and thus the force was oriented along the positive direction. Tau 1 1 is oriented along the positive one direction. The area is oriented along positive one direction, so the direction of force tau 1 2 is also along the positive y direction. But in this case, let's say A prime, B prime, C prime and D prime, the area is oriented along the negative one direction, so the force tau 1 1 is also oriented along the negative one direction. The second stress component I will write as this. The area is oriented along the negative one direction, so 1 I will write, and the force is oriented along the direction 2. But this time I will not draw this as tau 1 2. This is wrong. This is because the area of A prime, B prime, C prime and D prime is oriented along negative y direction. So that is why wherever I will write tau 1 1, it will oriented along the negative direction. And since in A, B, C, D, it is area is oriented along positive y direction, so tau 1 1 is oriented along the positive one direction. Now coming on to tau 1 2, since area 1 is oriented along negative one direction, so in that case negative 1 or negative I, negative 1 or negative I, so tau 1 2, it is along the negative 2 direction. This 2 represents the direction of force. So in which direction of force? In the direction 2, but along positive 2 or negative 2, that will be decided by this particular one. If 1 is oriented along positive, then 2 will also be oriented along positive. If 1 is oriented along negative, 2 will be oriented along negative. Now coming on to ABCD, if I write tau 1 2, the area is oriented along plus I or plus 1, and because of that tau 1 2 is oriented along 2 is representing the direction of force, so positive 2, because 1 is in positive direction. That is why 2 will also be in positive direction. Okay, so just we will do the derivation and the things will become more clear. Suppose I have I have any kind of system. I have this system, and this is a plate, this is a top plate, and this is the bottom plate, and fluid is flowing through this. Now I can define the x-axis to be like this, y-axis to be like this, and z-axis perpendicular to the surface on which I am writing. So this may be the coordinate system. But one thing that I would like to say, that if I take any area element like this, which is pointing along positive one direction, this is positive one direction, I can take some area element which may be pointing along the positive 2 direction, or I can take the area element which is oriented along some negative 1 direction, and I can take some area element which is pointing along some negative 2 direction. But apart from this, I can take some area element which is oriented along some normal, some randomly oriented direction, may not be in standard direction. So if I want to find what is the shear stress acting on this area which is oriented not along some standard direction but along some randomly oriented direction, so how can I find the total amount of shear stress on that, or total amount of stress on that area which is not along some standard direction? So in order to find that, what we do, the standard stresses tau 11, tau 12, tau 22 or tau 13, all these stresses are directly related to velocity gradients, which is called constitutive relation. So my aim will be to write the area which is oriented along the randomly oriented along some n. We want to write it in terms of tau 11 or tau 12 or tau 22 or so on in some standard direction. Okay, so this will be my aim, that the area which is oriented along some randomly oriented along some direction n, we want to write it in terms of the standard orientation. Okay, so suppose I have area which is oriented, or this is 1, this is 2, and this is 3. I will write it as A, B and C, and this is O. Now you can see that AOC is oriented along -3 and BOC is oriented along -2 and AOB is oriented along -1. So these three areas, AOC, BOC, AOB, are oriented along some standard direction. But if we talk about ABC, it is oriented along some direction n. This is the unit vector, and it is not the standard direction, not I cap, J cap, K cap. Now, if I want to find what is the total stress acting on this area, which is not in some standard direction, I want to represent it in terms of the stresses acting on AOC, AOB and BOC. Okay, this will be my aim, because the AOB, the stress acting on AOC will be directly correlated to velocity gradient by some constitutive relation that I know, that we will discuss further in this course, that the shear stress acting on AOC will be given by constitutive relation. But the stress acting on ABC will not be related directly by some velocity gradient, because there can be n number of possibilities of orientation of ABC in a particular flow field. So writing or resolving the total stress acting on some randomly oriented direction in standard direction is very important. Okay, so let us try to write how the forces are acting. So this is the first area, AOC. On AOC, I want to write where the force is acting. Suppose I want to write the forces acting on every surface in direction 1. So this is the surface AOC, and it is oriented along -3 direction. So if I have to draw the direction of force, how I can write that? Because it is oriented along negative direction, the direction of force will also be in negative direction. This is the correct direction of force. So this will be tau. The first index will give the direction of area, which is 3, and the second index will give the direction of force, which is 1. Note that we had not drawn it like this. This is wrong, because here this is area oriented along 3, this is correct. But if I write 1, I have to make sure that if the area is oriented along +3, then only I can draw the red line. But if area is oriented along the -3, I will have to draw the blue line. Okay, this must be taken care of. Now moving on to the area BOC. In the area BOC, we can see that it is along the -2 direction. So if I have to draw the direction of force on this area in direction 1, what I can say? It will be like this. Again, it is oriented along the -2 direction, so the direction of force will be this. Direction of area is 2 and direction of force is 1. Okay, again note that it is not drawn in this direction. This is not tau 2 1. This is not tau 2. Okay, now coming on to the third area. The third area itself is oriented along the -1 direction. So the force will be oriented along the -1 direction. This is the tau 1 1. Note that this is not tau 1. This is not tau 1 1, because area AOB is oriented along -1 direction, because this is positive 1 direction, this is positive 1 direction, and this is -1 direction. So AOB is oriented along the -1 direction, so the direction of force will also get reversed. Okay, these are the three things. Now considering ABC, the area which is not oriented along standard 1 2 and 3. In that case, if I draw, suppose this is at this point I draw, so the total force which is oriented, so it is oriented along direction n, and the direction of force is 1. So let us say it is oriented along some random direction n. Okay, so this is the total direction of, and we have to multiply all this by their area. This is S1, sorry, this is S3, because it is force per unit area. So this is S multiplied by S3, this is multiplied by S1, and this is multiplied by S2, and this will be multiplied by S. Okay, now what I can say, n is equal to n1 I cap plus n2 j cap plus n3 k cap. This gives the description of ABC. How ABC is oriented along some direction is given by the vector n. This n will give me the information about how ABC is oriented in a particular flow field. So let us apply force balance. Summation of all forces is equal to mass into acceleration. This is Newton's second law. Rate of change of momentum is equal to sum of all forces. It's proportional to acceleration. Newton's second law. So summation of all forces is minus tau 11 S1 minus, because let us say sum of all forces constitute of surface forces and body forces. So surface forces plus body forces is equal to mass into acceleration. Now what I can say, the surface forces are minus tau 11 S1 minus tau 21 S2 minus tau 31 S3 plus body force is given by, for this particular geometry, 1 by 3 into S into H. This is the volume multiplied by the density gives mass, multiplied by the density multiplied by the body force per unit mass, okay, is equal to mass is given by 1 by 3 into S into H gives volume into density gives mass into acceleration. This is the equation that I have got. Okay, now S is given by S1 is given by S into N1, S2 is given by S into N2, and S3 is given by S into N3. The component of ABC area in the direction 1 is given by S1. The component of ABC, which is S, in direction 2 is given by S2, and the component of ABC in direction 3 is given by S3. So this is something that we have got. So I can write tau 11 S N1 minus tau 21 S N2 minus tau 31 S N3 plus 1 by 3 into S H rho B is equal to 1 by 3 S H rho A. S gets cancelled. Tau 11 minus tau 21, tau 11 N1 minus tau 21 N2 minus tau 31 N3 plus 1 by 3 into H into rho into B is equal to 1 by 3 into H into rho into A. Now whatever element that I have taken, this particular element that I have taken, suppose it is very small. So if it is very small, then H will tend to 0. Now I want to get the pointwise description of the particular equation that we have derived. We have derived it for where H is very significant. Now we are saying that H is tending to 0, or the element that I have taken is very small. In that case, what will happen? Tau 11 N1 minus tau 21 N2 minus tau 31 N3. Sorry, there is one term that is missing. Here will be T1 N into S. Here also will be T1 N into S, that I have missed, plus T1 N into S is equal to 0, or I can say plus 1 by 3 into H into rho into B is equal to 1 by 3 into H into rho into A. Because H tends to 0, this will vanish. Because H tends to 0, this will vanish. So I will get tau 11 N1 minus tau 21 N2 minus tau 31 N3 plus tau T1N into S is equal to 0. T1N S is equal to T1S will get cancelled. So T1N will not become, sorry, this will not be there. T1N is equal to tau 1 N1 minus tau 21 plus tau 21 N2 plus tau 31 N3. So this is the relation that we have obtained. So the amount of, so what is T1N? This is force acting per unit area on area oriented along direction n is equal to n1 I cap plus n2 j cap plus n3 k cap, something like this. Force acting on area along this direction is related to stresses on area oriented along standard directions. Okay, oriented along standard direction. Now for any n, I can write it in terms of, for any area oriented along some along some n direction n, I can write it in terms of tau 11, tau 21 and tau 31. Okay, so I can write, and this tau 11, tau 21 and tau 31 is directly can be related to velocity gradient. And how it will be related to the velocity gradient in the case of Newtonian fluids? In the case of Newtonian fluids, we will discuss this in the upcoming course. For just for now, you just try to grasp this, that obtaining T1n in terms of tau 11, tau 21 and tau 31 is very necessary, because we do have information about tau 11, tau 21 and tau 31. We do not have information about T1n. So because of that, I have represented T1n in terms of tau 11, tau 21 and tau 31. And the description of n1, n2 and n3 comes from the area which is oriented along some random direction, because we will have information about that particular area by n. Any particular area oriented randomly, how I can identify that particular area? I will identify that area by the n vector. So we have information about n vector, we have information about tau 11, tau 21, tau 31. So T1n can be easily calculated. So the traction vector on any area in a flow field in any random direction can easily be obtained. Okay, now we will come, this is for the direction 1. Similarly, I can write for direction 2, T2n is equal to, and I will write for T3n is equal to, so it will come out to be, so I will write it in the directly in the matrix form, and from the matrix multiplication you can easily obtain. So if I have to write this for matrix, I will write T1, T2 and T3. And this will be tau 1, 1, tau 1, 2 and tau 1, 3. This will be tau 2, 1, tau 2, 2 and tau 2, 3. Tau 3, 1, tau 3, 2. And tau 3, 3. This is n1, n2 and n3. Sorry, this from tau 1, 2, this from tau 2, 1, this. This will become. Now in order to obtain T1, you can multiply this matrix with this vector, tau 1, 1 into n1 plus tau 2, 1 into n2 plus tau 3, 1 into n3, tau 1, 2 into n1 plus tau 2, 2 into n2 plus tau 3, 2 into n3, tau 1, 3 into n1 plus tau 2, 3 into n2 plus tau 3, 3 into n3. Now we will see the difference. There is no difference between tau 1, 2 and tau 2, 1. They both are same. Tau 1, 3 and tau 3. So this we will see in this further discussion. Suppose I have an element, and now this is oriented along 1 and this is orientation of 2 on this area and on this area. this is pointing along plus 1 direction, so the direction of area I will write as plus 1, and since it is oriented along plus 1, so the direction of force will be this, so the 1 will be written. For this, the area is oriented along plus 1 and the force will be oriented along 2. On this area, if I will draw, this is area is oriented along 1 but minus 1, so the direction of force will be negative and it will be written as 1. Now for tau 1 2 I will draw like this. Force is oriented along area is oriented along 1 but negative 1, so and force is oriented along 2 but negative 2. On this area, the area is oriented along 2 but negative 2, so the force is also oriented along negative 2, and this will be area is oriented along negative 2, the force will be oriented along negative 1. Okay, here the force is oriented along area oriented along positive 2, force oriented along positive 2 and 1. Okay, now what I will do, this is the axis and I will write the body couple about the axis which I have, this is O. So this particular force is passing through this axis, so there will be no contribution of tau 1 1 tau 2 2, no contribution of this. Now the forces that are going to contribute is tau 2 1 and tau 1 2. So let us write for this. Force is tau 2 1 into, let us say this is 2 times delta y and this is 2 times delta x. So tau 2 1, what is this length? 2 delta x into 1. This becomes the force, and the lever arm comes out to be, what will be the lever arm? This is the axis at O. There is axis perpendicular to the seat on which I am writing, and the force is acting along the positive 1 direction for tau 2 1, so the lever arm comes out to be equal to delta y. And if I am taking this direction to be positive, the same tau 2 1 is supporting this, so I am going to multiply this by 2. The tau 1 2 is in the opposite direction, so what I can say, tau 1 2 into 2 delta y into 1, this becomes force, and the lever arm comes out to be delta x. Okay, lever arm is the length which is perpendicular both to the axis and the force. So if tau 1 2 is the force and the direction of the axis is passing perpendicular to the sheet of paper on which I am writing, this length is the lever arm which is perpendicular to both force and the axis. Similarly, this is also perpendicular to both force and the axis, because this is the direction of tau 1 2 and the axis passes through O. So this will become like this. Now these are the two forces which are acting. Now this is equal to I alpha. So I comes out to be m into delta x square plus delta y square by 12. So density into delta x into delta y into 1, this becomes mass, into delta x square plus delta y square divided by 12. This is the general high school physics, how to find the moment of inertia. So the moment of inertia comes out to be delta x square plus delta y square divided by 12 into mass into alpha, I alpha. Now in this case we take delta x and delta y common, okay, and this is also multiplied by 2 because there are 2 tau 1 2. So tau 2 1 into delta x delta y into some constant which is 4 minus 4 into tau 1 2 into delta x into delta y is equal to rho into delta x into delta y into delta x square plus delta y square divided by 12 into alpha. Delta x delta y gets cancelled from both the sides and we get tau 21 minus 4 tau 21 minus 4 tau 1 2 is equal to rho into delta x square plus delta y square divided by 12 into alpha. Now take limit of delta x delta y tending to 0. In that case, the right hand side will vanish. 4 tau 21 minus 4 tau 1 2 is equal to rho into delta x square plus delta y square divided by 12 into alpha. This vanishes and we get tau 1 2 is equal to tau 2. There may be slight calculation mistake, but the ultimate result comes out to be tau 1 2 is equal to tau 2 1. So I can say that tau ij is equal to tau ji. Note that the significance of rho into delta x square plus delta y square divided by 12 into alpha became equal to 0 only because delta x and delta y tended to 0. So only because of that we have come to the conclusion that tau 1 2 is equal to tau 2 1. Similarly, I can derive for tau 1 3 is equal to tau 3 1 and tau 2 3 is equal to tau 3 2. So tau ij is equal to tau ji. In general, we can say that. If and if no body couple is present, in that case we can say that. Okay, so